The electric field that we've been talking about over the last several days is what we call a non-uniform electric field. It means it's not the same value in every place. The position affects what the field strength is. A non-uniform electric field would look like this, surrounding a positive producer. The density of the field lines, or in other words, how close the field lines are together, indicates the strength of the electric field. So in other words, you would say that the electric field right here is stronger than the electric field right here. It's a non-uniform electric field. It varies depending upon location. Now, what we're going to talk about today are uniform electric fields. A uniform electric field exists between, bear with me on this, two charged metal plates. And in other situations as well that can approximate two charged parallel metal plates. So here's two metal plates. They're charged. One is charged negative, let's say. One is charged positive. Doesn't matter how they got the charge, they're charged. There is an electric field between those two plates that goes away from the positive and toward the negative. That electric field in this case would point upward, away from the positive toward the negative. That's a uniform electric field. It's uniform, we know that because the field lines are parallel to each other. In other words, unlike in the first diagram, the field strength right here would be exactly the same value as the field strength right there, a uniform electric field. Now, there's lots of places in technology where there are two charged metal plates that are parallel that contain a uniform electric field between them, but not so much on a macroscopic level. We don't see this literally so often. We do see it. Okay, you go to an amusement park and you see bumper cars. You have a metal plate at the top, a metal plate at the bottom. There's an electric current that goes through the car between them. There's a uniform electric field between those two charged metal plates. But we don't see something like that often. More often we see an approximation of two charged metal plates. Like for instance, on a day where it's raining and it's about to thunder and lightning, a cloud is charged negatively and it induces a temporary separation of charge in the earth, which is positive, which approximates two charged metal plates. We could treat it the same way. So even if it's not exactly two charged metal plates, we can often treat things like a cloud on the ground as two charged metal plates, a uniform electric field. Now, the equation that we learned to describe an experiencer, okay, E is equal to F over Q, applies if we have this equation, if we have this non-uniform field. Let's say we have an experiencer right here. Okay, the equation that we learned, E is equal to F over Q, is valid in that situation. But it's also valid in this new situation. As long as I have an experiencer, it doesn't matter whether it's a uniform or a non-uniform field. The equation translates. The producer equation, on the other hand, does not translate. The producer equation that we learned about is only valid for a non-uniform electric field. In other words, we can't use this equation in our new scenario. We can only use it in the scenarios that we've used it thus far. This new scenario where we have two charged metal plates with a uniform electric field, we need to come up with a new producer equation. Our experiencer equation is the same for both. Our producer equation that we used is still valid, but not for this new situation. We need a new producer equation. So what does the new equation look like? The equation that is, well, we'll call it our producer equation for a uniform electric field, looks like this. E is equal to delta V over delta D. A couple of the variables here you're not familiar with. Let me redraw this. Let's make this time a positive plate on the top, a negative plate on the bottom. This time the field will point downward, away from the positive toward the negative. You can still see that it's a uniform electric field because the field lines are parallel. The field strength everywhere in between those plates, here, here, and everywhere else, is exactly the same. The electric field value is delta V over delta D. Now delta D is going to represent the distance between the plates. Be very, very careful here. Some people will, if there is an experiencer in between the plates, want to say delta D is the distance that the experiencer moves. That's not the case, ever. Some people will want to say, oh, delta D is the distance of the experiencer from the top plate. That's not delta D ever. Some people will want to say it's the distance from the bottom plate. That's not delta D. This is a producer equation. Delta D relates to the producer, and the producer is the two parallel plates. So delta D for us, no matter what numbers we're given in this question, delta D will always be the distance from the top plate to the bottom plate. They will try to trick you sometimes. They will try to trick you by putting in a number for the distance that the charge moves or something like that. That's not delta D. This is not a displacement. This is not a distance traveled. This is a distance between the top plate and the bottom plate. And it's going to be measured in meter. Now, delta V, that's the trickier one, delta V. Delta V stands for potential difference, and that's a brand new term for you. Let me define potential first, before I define potential difference. Potential is the energy per unit charge, the energy per coulomb of charge. The energy per coulomb, not the energy, not joules, but the energy per coulomb. So the amount of energy that each charge has. Let's say there's 20 people in this room. Okay, 20 people in this room. Got it? People are analogous, in this little analogy here, people are analogous to charge. Money is analogous to energy. Got it? In the analogy that I'm going to give you, people are charge and money is energy. Okay, so there's 20 people in this room. How much charge do we have? 20 coulombs. Okay, got it? Each one of you has $5. How much energy does each one of you have? 5 joules, right? Okay, how much energy do we have total? We have 100 joules, right? $100, 100 joules. Got it? That's energy. That's not potential. That's not potential difference. We have 100 joules of energy in this room. Potential is the energy per coulomb of charge. How much energy do we have per coulomb of charge? Or how many dollars per person do we have? 5. So our energy is 100, our potential is 5. Got that? It's not the energy, it's the energy per coulomb of charge, or the energy per person, the money per person. Okay? That's potential, not potential difference, that's just electric potential. Okay, now let's go to 7-Eleven. Each of us spends $2 on a Slurpee. How much energy do we have now? We have 20 people. We just spent $60. Sorry, we just spent $40. $2 a Slurpee. How much energy do we have now? How much money do we have now? 60. That's my energy, right? Okay, that's my energy. My energy per coulomb, or my money per person, is what? What is it? 3. So my energy was 100, now it's 60. My potential was 5, now it's 3. Got it? What's my potential difference? 2. It's the difference in energy per coulomb of charge. The difference in money per person. Got it? The difference in energy per coulomb of charge between the two plates. The potential difference is measured in joules per coulomb, because it's difference in energy per coulomb of charge, but we often just abbreviate that with a big V, which means volts. A 1.5 volt battery has a potential difference of 1.5 volts. The difference in energy per coulomb of charge between the positive terminal and the negative terminal is 1.5 joules. Okay? Go to 7-Eleven. Start with $5. And with $3, the difference in energy per person, difference in money per person is $2. The potential difference is $2. Okay, we're going to measure the difference in energy per coulomb between the top plate and the bottom plate, and we're going to call that, in this context, the potential difference. Now I'm going to summarize what we just did with these three equations with a little Venn diagram. You guys know what a Venn diagram is? With circles that show similarities and differences between things. I'm going to draw a Venn diagram around my three equations here. The first one is going to be the first producer equation that we learned, E is equal to KQ over R squared. The second one I'm going to write down is the experiencer equation that I learned earlier in the week. E is equal to F over Q. And the third one is going to be the new equation that I just learned, E is equal to delta V over delta D. The top one and the bottom one are both producer equations. But the top one is a producer equation for a non-uniform field. The bottom one is the new one for the uniform field. Let's draw our circles around this to make this into a Venn diagram. The first two equations get circled by blue. Blue is going to represent a non-uniform electric field. We have a situation like this, where we have a charge producing an electric field, but those electric field lines are not parallel to each other. In other words, the field at this point is different than the field at this point. It's a non-uniform electric field. I'm allowed to use either one of these equations in that situation. We did, over the last couple of days, use those two equations in this situation. The bottom two equations, I'm going to circle in green. The green represents my uniform electric field. I'm allowed to use either of these equations in the new situation of where I have parallel field lines. In a situation like this, let's make the top plate positive, the bottom plate negative. Situation like this, where we have an electric field right here, it's exactly the same value as the field here, which is exactly the same value as the electric field here, a uniform electric field. So, if you know something about the producer in a non-uniform field, use the first equation. The experiencer in a non-uniform field, some little experiencer that I put right here, use the middle equation. If I know something about the producer, the two parallel plates in the second situation, the uniform field, then use the last equation. If I know something about the experiencer, some little experiencer right there, then use the middle equation. In other words, what we're saying is the first equation and the last equation are unique to non-uniform or uniform, but the middle equation can be used whenever we want, as long as we have something to experience the field. Uniform or non-uniform, doesn't matter. One example, and then we're going to finish it off here. It says a potential difference of 20 volts exists between two charged parallel plates that are 3 centimeters apart. Top plate is positive, top plate is negative, bottom plate is positive. Circle the centimeters because we don't want to be in centimeters, we want to be in meters. Just say uniform or a non-uniform field. Two parallel charged plates. This is a uniform field, right? Let's draw it out just to kind of help us to internalize the fact that it's a uniform field. Top plate is negative, the bottom plate is positive. The field goes away from the positive toward the negative. Field lines are parallel. It is a uniform electric field. Which two equations am I allowed to use when I have a uniform electric field? Of the three, equation 1, equation 2, equation 3, which ones am I allowed to use if I have a uniform electric field? 2 and 3. Right, the bottom two, E is equal to F over Q, delta V over delta D. What do I have more information about here in this question, question A? Do I have more information about the plates themselves that cause the field, or something in between the plates that experience the field? Dylan, what do I know more about here, the producer or the experiencer? Yes, I know more about the plates themselves, the potential difference between the plates, the difference in energy per coulomb between the plates, and the distance between the plates. I know more about that than some experiencer that's in between. Maybe there's something in between. Maybe there's. I don't even really know if there's anything there. Got to use the producer equation here. It's the only thing I have information about. So let's say delta V over delta D. Delta V is 20 volts. And delta D is 0.300 meters. When I do that math, I get 666.666. What would the units be for this? Yep. Yes, it is. Thank you. 0.03, not 0.3. It still gives me 666.6667, right? What would the units be? Anybody? Not coulombs, no. It's the electric field. No, that's energy. Remember we learned earlier we've been using newtons per coulomb the whole time? It's fine. You still use newtons per coulomb if you want, but now we could also use, if we wanted to, volts per meter, right? Volts over meters here. So either one of those is correct. 667 newtons per coulomb or 667 volts per meter, whatever you feel more comfortable with. All right, question B asks me to determine the electric force experienced by a proton if it was between the plates. If we look back at those three equations, we know the first one still isn't valid. It's never going to be valid here, because that's only valid in a non-uniform field. The last two are valid in a uniform field. We've already used the last one. Let's try the middle one now. Let's try that middle one. E is equal to F over Q. We want to solve for force here, so let's rearrange that to solve for force. F is equal to Q times E. The charge of a proton is 1.60 times 10 to the minus 19 coulombs. The electric field that we just found is 666.6667 newtons per coulomb or volts per meter. That gives me an electric force here of 1.06667 times 10 to the negative 16 newtons, which is 1.07 to 3 digits times 10 to the negative 16 newtons. Now, we don't have a direction here. Let's figure out the direction. We get a positive charge in here, right? It's a proton. We got a positive charge with the field up. Which way is the force? Which way is the force? It is with the field. Are you sure? Positive, the force is with the field. So the electric force has got to be upward toward the top plate. And finally, the last question just asks us for the acceleration. We know how to do this already, right? We're almost Yoda strength here now. Like we're almost in a Yoda league here right now. Right? We've done this long enough. The force is with us. We know what to do with the force. We know how to deal with the force, right? We have the force. The force is with us. We want to find the acceleration, use the force. The force at 666.6667 newtons per coulomb or volts per meter divided by the mass of a proton, which is 1.67 times 10 to the negative 27 kilograms. We do that, we get a value of 6.39 times 10 to the 10, and that's going to be meters per second squared. Now, which way would it accelerate? Well, the force is upward, so the acceleration would be upward as well. Sorry, mistake there. The answer's right. Remarkably, the answer still came out to be right. But the force that we got here is 1.06667 times 10 to the negative 16 newtons. And lo and behold, we still get 6.39 times 10 to the 10. We're going to get you to finish off worksheet number 8 now, which consists of questions 10, 11, and 12.